Hi, kids. This tutorial is meant to help you gain a rich understanding of the concept of density. So there's our goal. That's at the end of the day, I want you to walk out of here with a real deep sense of what density is and how to calculate it. We have three objectives in order to achieve that goal. Our first objective is that we are going to determine the density of distilled water, and we're going to do that experimentally. Sure, we could look it up on the internet and get it in 2 seconds, but I want to walk you through it experimentally so you can really understand how we know this. Our second objective will be to determine the density of 3 cubes of unidentified material. And you see those down there in the lower right. I'm purposely not telling you what they are because it's kind of cool to find out their densities. And then with that information, you might be able to make some educated guesses as to what they are, what materials those 3 cubes are made of. More on that another day. Our third objective is to determine, once we know the density of these blocks, whether or not they will sink in water. So we need to achieve the second objective before we can do the third objective. That means, obviously, we're going to need to know how to calculate density. And I know that probably the vast majority of you right now know this because we've done this in class once already. But if not, this tutorial will help you, and you can pause it and work at your own pace and learn it really well. I like to tell my students that when you forget, as a high school student, when you forget this formula, it breaks my heart. And that's because if you break a heart in half in this way, it kind of looks like an M over a V. This is one of those little cheesy tricks that we teachers like to use, but it helps, right? And use it for a little while now, and then before you know it, you won't even need to think about it. When a future teacher asks you to calculate density, you won't even give it a second thought. You'll just know it's mass divided by volume because you will have used the formula enough. So now that we know that is the mathematical operation for calculating density, we can go on and start working towards objective number 1, to determine the density of distilled water. Well, as you know, we can't just go throw water on a scale. It doesn't work that way. So we have to use a graduated cylinder, which you see there on the left. Now remember, a graduated cylinder is the correct tool to use whenever you're measuring the volume of a liquid. Okay? But first, before we go and put water in this graduated cylinder, we probably ought to know the mass of the cylinder without water in it. And I want you to maybe pause the video right now and ask yourself why. Why is it important to know the mass of this graduated cylinder before we even put water in it? Go ahead, pause the video, and make sure you give yourself a chance to think that through. Okay, so we go ahead, we put the graduated cylinder on the scale, and we get a value of 127.74 grams. Now, we're going to go ahead and we're going to fill that cylinder with 100 mils of water. We're going to pay attention to our rules that we have to follow when measuring a liquid in a graduated cylinder. And there are 2 important rules to keep in mind. You should always be eye level, always. And the cylinder should always be on a flat surface when you're making your measurement to see if you have what you need. The other rule is that you need to be mindful that when you put water in a narrow tube like this, it does form something called a meniscus at the surface. The water has a curvature to it because water has this property of adhesion, and it will start to climb up a little bit on the inside wall of the graduated cylinder. And that forms that curvature that we call a meniscus. When you're making a measurement with liquids in a graduated cylinder, you always pay attention to the bottom of the meniscus, not the edges where it reaches up a little bit higher. All right, moving on. We go ahead and we put that graduated cylinder back on the scale, this time with the water in it. And we get a new measurement of 227.97 grams. Okay, great. But now we have to wonder, well, what is the mass of the water itself? We knew what the mass of the cylinder was. We knew what the mass of the cylinder with the water was. how do we go ahead and calculate the mass of just the water itself? Okay, pause the video, make sure you know how to answer this on your own right now, and then come back and play to get the answer. Well, mathematically, it's very easy. We take the mass of the cylinder with the water in it, we subtract from it the mass of the graduated cylinder alone, and that's going to yield for us the mass of the water. Now, we have to remember that there is 100 milliliters of water in there. And I want to challenge you right now to think about that for a moment. So I have a question mark here. This would be a good time for you to pause it and pause the video and ask yourself, do we really have full confidence that we have 100 milliliters of water in there? More on that in a little while. We have to remember that we filled that graduated cylinder, and we are humans, and human error always plays a role. We can almost certainly say that we do not have exactly 100.00 milliliters of water in there. Okay, but going with that, that is our best assumption at this point. We know what the mass of the water is. That we can be confident in. The digital mass scale measured it for us. And if that number is off at all, then it's only off a little bit because maybe the scale is a little bit miscalibrated. But we can have pretty high confidence in that number. We don't have as much confidence right now in the volume, in the 100 milliliters. Okay, still, nonetheless, when we divide 100.23 grams by 100 milliliters, we get a value of this. And we have to remember that our units carry through. We are not able to cancel out those units because they are not the same units. So grams remains in the numerator, milliliters remains in the denominator. And there is our calculated value for the density of water. I want you to realize here that that number is awfully close to 1. It's so close that it should raise suspicion. A little light bulb should go off here. And that's going to bring me back to what I said earlier. Remember when I said we do not have complete confidence that we had exactly 100 milliliters of water? Human error probably played a role. Well, here's where I'm going to step in and kind of just go ahead and tell you that we actually probably had 100.23 milliliters of water in there. And how do I know that? Well, because as your science teacher, I'm going to tell you now that the density for distilled water is 1.0000 grams per milliliter. That is the density of water. And by the way, there's no mistake. That's not just some random coincidence. We humans made it that way. When humans were trying to design something to measure the volume of liquids, they had to come up with a standard unit of measurement. And what they did is they said, okay, well, let's go ahead and let's define this thing called a milliliter. And let's say that a milliliter is the amount of liquid water we need to equal 1 gram of mass. So therefore, with that logic in mind, the density of water has to be 1 gram for every milliliter. I hope that makes sense. If not, you should check in with me when we're in class and we can have a one-on-one discussion about this. It's not too different from what they did in the United Kingdom hundreds and hundreds of years ago when they needed a way to measure length. They had all these people out on their land walking around, pacing their property and trying to sell each other pieces of land. But the problem is people walked at different paces or different strides. Some people had bigger feet than other people, so they needed a standard way to do that. And what did they do? I think a lot of you know this story. They used the king's foot as a standard unit of measurement for length. And that's not too different from what we're doing here. We are saying that a milliliter is the amount of water you need to equal 1 gram of mass. The neat thing about this, and I wish we could play with other liquids, and maybe one day we will, because that's not going to be true for other liquids. If we measure 1 milliliter of vegetable oil, for instance, it would not equal 1 gram. I'm wondering if you would know if it would be less than 1 gram or more than 1 gram. We'll have to do that in class one day. Okay, now we're going on to our second objective. Now that we know the density of water, now we have to go ahead and figure out the density of these 3 blocks. I went ahead and I arbitrarily numbered them, number 4, number 8, and number 12. And remember, that's because I have a set of 12 blocks, and I chose these 3. We'll someday work with the other 9. We're going to go ahead, we're going to put block number 4 on the scale, and we get this measurement, 45.39 grams. Then we're going to go ahead and put block number 8 on the scale, and we're going to get a measurement of 7.34 grams. And finally, we're going to put block number 12 on the scale, and we're going to get a value of 20.38 grams. All right, we probably should record that information. And so we do that neatly in a data table, as any good scientist does. It's always good to organize your data and not just like throw it on the back of some paper, right? Okay, well, we're halfway there. If we want to calculate the density of these blocks, we need to first figure out their volume, right? Okay, so calculating the volume of a cube is a pretty simple calculation, and every ninth grader should be savvy with this. Pause the video and see if you can remember it on your own right now, and then come back and let's see if we can figure this out. Okay, well, the volume of a cube is its length times its width times its height, or L times W times H. So we need to figure out the length, right? And we're going to get ourselves a metric ruler. We're always going to use metric units. And we're finding that these cubes have a length of 2.5 centimeters. Now, it's important here to note that, and look at my number, look what I wrote. You don't write down 2.5 centimeters. You actually should write down 2.50 centimeters. And you might be wondering why. Well, here's the thing. In science, when you use a calibrated instrument like a ruler, you should always write down all the numbers that you're confident in, and then you should write one more number that's a little bit of a guess. I can tell with my eyes that the length of this cube is 2.5 centimeters. I can't tell, is it 2.51? Is it 2.50? Is it 2.56? I'm not really sure of that last number because this instrument isn't calibrated to that level of precision. So my 0 is a guess, and I always should write in a guess to communicate that to my audience. That way, when other scientists look at my results, they know that I was confident in the 2, and they know that I was confident in the 5. Another way of saying this is I'm letting my audience know that I'm confident down to the 10th of a centimeter with this instrument. Okay, try to keep that in mind as we go out throughout the year, because it's something that I'm going to want you to get better and better at, so that by the time you go off to your sophomore year in biology, you won't have to really think about this anymore. Okay, here's the beautiful thing about cubes. If you know the length, then you know the width, and you know the height, because they're all the same. And some of you communicated that to me the other day, so I feel confident that that's not any mind-blowing thought for you guys. You guys are pretty clear on that. All right, so that means we don't have to go on and measure anything else. We already have those other 2 dimensions. So now we can go on and use that formula and multiply 2.50 centimeters times 2.50 centimeters times 2.50 centimeters. And we find that we get a value in our calculator that says 15.625 cubic centimeters. All right, well, I hesitate a little bit here. I don't know if I want to drop this on you guys, but the thorough part of me says I should bring it up at least, and we can talk about it more another time. Technically, this number, this answer that you see here, yeah, it's what my calculator shows me, but I can't really write all those numbers down. Because remember, in my original measurements, if you think about it, if you look back to your original measurements, we weren't confident in that 0, right? So we have 3 numbers, a 2, a 5, and a 0 that we had in our measurement. That's 3 numbers. Our final answer can't be more precise than that. So it turns out that what we really ought to write down, if we're being good scientists, is 15.6. Right? How did I get that? Well, I just dropped the 2 and the 5. Believe it or not, that is what you're supposed to do. Okay, so there's my answer for the volume of these cubes. Great. Now we can go ahead and we can put that information on our data table. And you know what we're going to do next? You can probably see it here. We're going to go ahead and we're going to calculate the density. Okay, remember that formula. Density equals mass divided by volume. Okay, so there's how it looks operationally. And when we go ahead and we calculate those numbers, we get longer numbers than this in our calculator, but we only can have 3 in our final answer. This is interesting because if you look at block number 4 for a minute, you'll see that we were able to write down 4 numbers for the mass for cube number 4. We wrote down a 4, a 5, then we had a 3 in the 10th place and a 9 in the 100th place, right? So our digital mass scale was pretty precise. It gave us more numbers than our measurements did for length. But that doesn't matter. When we go on and we do our final calculations, our final answer cannot be more precise than our least precise measurement. So in this case, our least precise measurement is our volume, 15.6. Therefore, our density can't have more significant figures in it than that. Okay. We're going to go ahead, we're going to put that in our data table, and we're getting close. Now we're moving on to objective number 3. And this is where we're going to determine whether or not each cube will sink or float in water. So that means we have to go back and remember what the density of water is. And there it is, 1.0000 grams per milliliter. Well, here's something a little, I don't know if you want to call it a fun fact or just something that you have to be mindful of. This can be a little confusing for students because water is a liquid and you can't shape water unless you were to freeze it, but then it takes on different properties. When you freeze water, it expands a little bit. But just imagine for a moment if you were somehow able to shape liquid water into a cube. I know we can't do this, but just imagine we could. If you took 1 milliliter of water and you molded it so that it had the shape of a cube, it would be exactly 1 cubic centimeter. Pretty cool. That means that we could also think of the density of water as 1.0000 grams per cubic centimeter. And why do I bring this up? Well, because now it makes it really easy to compare the density of water to the density of those 3 blocks, because now your units are exactly the same across the board. So, I didn't want to show you that yet, darn. Maybe you just saw the answers, but if not, can you make a guess here? What will block number 4 do if we were to put it in water? What will block number 8 do, and what will block number 12 do? Well, if you guessed this, then you are correct. Block number 4, for instance, has a density of 2.91 grams per centimeter cubed. That's a greater number than 1.000 grams per centimeter cubed. So therefore, block number 4 will sink in water. And we can test this experimentally. We will probably do this in class one day soon. Block number 8 has a lower density than water. So if we put it in water, it should float. And we will test that as well. Block number 12, while close, it is denser than water, and so it should sink. If we had a huge column of water, it would be interesting to see, and maybe we should do this experimentally someday in class and have fun with it. We should see, would block number 4 sink faster than block number 12? That would be cool to check out. And maybe we'll do that one day. Okay, so there's our 3 objectives that we just achieved. And hopefully by achieving those objectives, you can confidently say that you understand the goal. Now, like a lot of our lessons, if you think you get this and it's easy breezy for you, then you're done. Move on and you'll demonstrate that you understand this when I test you on it someday. If you're not feeling 100% confident, then I encourage you to look over this again, either right now in class or at home for homework or whenever during your study hall. But you should go through it at your own pace and make sure that you understand it well. Thank you.